Nick is currently the Director of Labs at Impact Exploration Services. He created and built a new technical division to expand Impact services to include XRF, XRD, program pyrolysis, and capillary suction tests. He's responsible for maintaining the lab's technical standards, establishing relationships with clients, as well as mentoring and cultivating the staff. Prior to joining Impact, Nick worked for Weatherford Labs as a data analyst and project manager. He earned a bachelor's in environmental physical sciences from Black Hills State University in 2012, and he will be giving us a talk today about the investigation of clay content as being a cause for suppression of pyrolysis Tmax maturity data in the Wolfcamp B formation. So I will turn it on over to Nick.
Thank you very much. I hope everybody can hear me all right. First off, I want to say thank you to the OCGS for inviting me to present today. It's societies like this that keep us together during these tough times and allow us to share ideas and communicate, especially when a lot of us are still trapped at home and haven't made it back to the office. It kind of gives us an outlet. So thank you for this. Let me go ahead and get into this real quick. First off, usually I'm an unconventional presenter, but in this case, I'm not going to be able to see your questions while I'm presenting, so I'm going to have to wait until the very end to ask things or answer the questions that you have. So let's talk about clay content and how it can affect your Tmax data. This was a project that stemmed out of another research project we were doing with Eddington at the point. We were looking at geochemical signatures within the hydrocarbons through extraction, and when we started putting data together, we started seeing an anomaly, which kind of led us down this path. So first off, really Eddington brought us on to assess the well for organic richness, economical production. So we took 10-foot cuttings and analyzed it XRD bulk, XRF, and pyrolysis initially, so we can outline the zones of interest. Once we started seeing this anomaly happening, we kind of focused our attention to what was causing this regression in our thermal maturity. Was it just the clay matrix? Was it the depositional environment? Or was there a hydrocarbon component there that wasn't seen on the surface? We also used mass spec during the drilling process, which I'll show that data later on. And during the evolution of this continuing project, we're looking at analyzed produced fluids for the whole oil, so we can understand and see the different geochemical signatures during the stages of production, pre-shut-in and post-shut-in as well. But unfortunately, that is still proprietary information that we can't share in this presentation. So the location of this well is in Loving County, which is a Delaware Basin well. We focused on the Wolfcamp A, Wolfcamp B formation for this client. We analyzed 1,700 feet vertical section, and as mentioned before, these were 10-foot spot samples. I want to clarify on the spot samples, these were caught at depth, and these aren't interval samples, so that we can eliminate a lot of that smear that we see in those homogeneous samples when we're not collecting that spot. These were OBM samples, so that comes into play because we can't evaluate what our free hydrocarbons are in the system due to it being masked by the OBM. So that was information that we weren't going to be able to use. Just real brief, I'm not going into a lot of detail here. For this location, the deposition was a distal portion of a semi-enclosed basin. It was primarily siliclastic and carbonate gravity fed, and the carbonate beds were mapped to the central basin platform. It's really important for me to kind of go into the details of our analysis because we want to eliminate any potential flaws, any issues that could have arisen in the lab or the analytics, so we can eliminate that as a possibility. As I mentioned before, these are oil-based mud, so we cleaned them with DCM at ambient temperatures. The reason we do it that way is we don't want to alter any of the matrix. We want to change any of the properties that we've seen slightly with different methods, especially when you start introducing heat during like a Dean Stark apparatus and so forth. We analyze the samples doing the classical pyrolysis method and also the Hawk PAM method, which I'll go into detail here in a little bit. The instrument we use is the Hawk, which is produced by Wildcat Technologies. We analyzed the mineral matrix using XRD bulk and clay. We analyzed this on 4-micron homogenized samples, and we just did direct measurement. We used the Reynolds method of suspended gravity for the clays. And then as far as XRF, we evaluated on 12 majors and 20 traces. This is a bench top system, so it's not a handheld. This is a vacuum sealed unit that's going to eliminate a lot of the air interference. And the main reason I'm going into really the technology is so you can see that these aren't, black box tools. These are, lab grade instruments that we're using here. So we have a high confidence of the data coming out. As long as everything's prepared correctly and done correctly, this is going to eliminate a lot of the possibility that cross-contamination or issues with the data itself. So after we analyzed everything, we started fitting into our logs charts so we could start evaluating what we had. We started seeing something interesting for our Tmax. So a quick breakdown, this is going to be our XRD data. Brittlness index, which is for us, it's just simplistic. It's an inverse ratio clays. Our Tmax, our TOC, our S2, our kerogen, the hydrogen index, and then we put some organic proxies here for XRF to kind of help us evaluate more. So as far as the TOC, anything over 2% is going to be that gray portion. Anything below is going to be green. Same as the S2, so anything that's over 2 milligrams per gram is going to be red. Anything below is going to be green. And the reason these are the main cutoffs is there's a lot of literature saying anything above these values is going to be more of an economic and a shale play. So these are the set rules that we apply in our charts. Now, when we look at our Tmax, we start off in this gas window at 11,500 feet. But we see this gradual decline as we're coming down the formation until we hit this marker here and we come back out and our thermal maturities increase once again. And then we have this gradual decline once again. Now, the reason this is important is your thermal maturity should increase or will increase with depth. And we're seeing the exact opposite here. So this really brought up a lot of questions when we were sitting together trying to figure out why are we seeing this decrease. And we have to figure out, is this a byproduct of the samples? Is this a depositional thing? Is this a one-off occurrence that is not going to affect our production, or not my production, but their production overall? So once we start kind of digging in the data, we start seeing some trends. But before I really get in those trends, the S2 average for the 1,700 foot section was 4.51 with the average TOC of 2.06% weight, and our hydrogen index was 221. So we're looking at a mixed system as well. So once we kind of started diving further in and trying to figure out why we have this regression in Tmax, we started applying elemental proxies to see if anything happened after deposition. There was no positive correlation there. So that was ruled out, that there was an occurrence after deposition that affected these for some reason. So we started looking at the matrix of the rock. And the one thing that we noticed was if we separated the clay tract from our mineralogy and overlaid it with our Tmax, as you see in this log right here, we almost have a perfect correlation. We tried to do some R-squared values on this, but there's so many variables that go into this that we weren't able to get a decent R-squared value to present. So visually, looking at it, we could see that there's an effect going on here. Anytime that we had an increase in clay, we had a decrease in Tmax, so cause and effect. But was it just the clays that were affecting this regression, or was it heavier oils trapped in the sample itself? So that's really we need to figure out, is it something that can be figured out through just a quick extraction beyond the DCM, or is it something that is in situ and is more driven by what the deposition was and an occurrence after deposition? So we're started off on the easy side. Some people would think the clays are the easy side, but we went and want to look at the heavy hydrocarbon impact for these samples first to see if we got a quick answer there. As I mentioned before, I really kind of want to get in these methods real quick so that we're all on the same basis. Our methods are 25 degrees Celsius per minute, which is the industry standard for the classical pyrolysis. A lot of people have seen pyrograms, so this is kind of rehash on some old stuff that you know. But the main reason I put it up here is I really want to show you how the Tmax is calculated. It's calculated off that S2 curve, the pinnacle point, and what the temperature is in the oven at that point. So heavy hydrocarbons can pull that Tmax to the left, which is going to lower our Tmax down. As far as the Hawk PAM, this is a method that Wildcat has really put out in the last couple of years. The PAM stands for Petroleum Assessment Method. And this is their approach to really start breaking down that S1 number into more usable numbers for us and kind of equate it to Sarah. With 4 oil components and the K1, which is our typical S2 peak in classical pyrolysis. As we can see on here, we're breaking these into different carbon chains loosely. We have our saturates and aromatics fraction, and then our oil 4, which is typically what's going to give us that shoulder on our S1, which is that immobile oils, is going to be those polars, so your asphaltenes and your paraffins. So this sample was ran, I presented this sample because it was the best explanation of what we saw going on with classical pyrolysis versus Hawk PAM. As you can see above on the first pyrogram, we start seeing this like slight S1 carryover. We're not really seeing a bimodal peak that is a super big red flag. We do see that our baseline never returns down the bottom between our S1 and our S2 numbers. So that kind of gives us an indication that there is a heavier component there that can't be stripped out with the DCM. And it's something that we have to do another cleaning process or go to this Hawk PAM method. Now, originally on this sample, when we analyzed it, we got a Tmax of 438 degrees Celsius. Our S2 number was 6.34, but when we went to the Hawk PAM, our Tmax increased to 440 degrees Celsius. And the more startling aspect of information here is our S2 number actually dropped to 2.57. And the reason this is big is when we don't have an S1 number, we tend to go to the S2 number as looking at potential and equating barrels per acre foot, hypothetically. And when you have a 6.34 versus a 2.57, you're going to grossly overestimate what your potential reserves are or what your potential are. And it could throw off, decline curves. It can throw off, what your GORs and your IPs are going to be for those wells. And that leads to more questions with, did we do the completions right? Was there something wrong? When in all reality is we had skewed data from this heavier component. The other thing I really want to point out on the Hawk PAM is we have this perfect geometry for our K1 peak, which is that S2 peak, where we are really elongated on this one. So the next impact we want to look at is the clays. We only saw a 2-degree change on average for the Hawk PAM. That's not enough to sway these samples as far as they've gone. And when we're evaluating, a 2-degree change can put us on the edge of, a condensate window or a peak oil window. So it's not a large enough movement for us to be overly concerned about our production. So the next part, we started doing clay speciation on all the samples to see if we could find this trend. And the samples I have up on your screen right now are 5 consecutive depths. And remember, these are 10-footers. And I've also put the Tmax in here so we can see the clay change and how our Tmax changes as well. When we look at our IS, which is illite smectite, or the swelling component, the smectite component of these samples, we see these increases and decreases. And when we see a decrease from this 12.8 to 8.2% by volume, we have a 5-degree change in Tmax. Now that's massive. That can sway us one way or another very quickly and can alter the way we look at these wells for our thermal maturities. And then when we had an increase again, we had another 5-degree change going back down for our Tmax. So just in 20 feet right here of samples, we have an 8-degree change in our Tmax. That can put us completely out of the thermal maturity window that we want to be in for the acreage that we're looking at. We also did some SEM images as well to just verify the clay structures and kind of just back up the information that we did through the XRD. It's always good to have the extra data in there when you're doing research projects and doing high-end projects like this, because having a well-rounded answer is going to be better than just having that one portion. Sorry. So looking at the overall picture of what we have going on here, we see a 2-degree change average for the heavier components, but we're seeing a maximum of an 8-degree change when we're looking at our smectite with our total clay effect. Now, in conjunction with those, we could be looking at a 5-degree change all the way up to a 10-degree change in our Tmax. But the main driver here is going to be that smectite portion in our total clays, which is going to be more related to our depositional controls. Even though we had some hydrocarbon controls in with the maturity aspect, we had some heavier oil components that weren't broken down to methanes and ethanes. So in conjunction, they both affect it, but primarily it's going to be that smectite within your clays. So earlier I said, we use mass spec, and I know a lot of people are, sitting back and asking themselves, well, you have gas data when you drill. So what do the gas data show you? We use mass spec on this well specifically because we want to see the full complex. We just didn't want to see C1 through C5 and a very basic wetness balance ratio. This was a first well in their program. They wanted to make sure they understood what they had going on in their acreage. And so we kind of threw the kitchen sink and everything at this project. As we see in the upper hole that we didn't analyze, we had some very detailed, very great gas coming off. So this first column right here is going to be our C1 through C4, so our lighter components. And then the second column right here is going to be our C5 through our C10. So more looking at what our liquid portion is. And I group C5 in there just due to atmospheric conditions when it comes to surface. It can drop out or it can be in gas solution depending on what's going on at surface. So I typically add it in on the heavier components. We also see great benzene, great toluene numbers, and these are important because this is going to help us understand our water saturations as well. Now, it doesn't give us a fixed number. It only allows us to see the general trends, but still very good information. Well, when we switched over to OBM, a lot of the signals got masked by the OBM just because it's a heavier constituent and it's not allowing everything to be broken out the way we want to. And the other issue we had was the agitator in the pit wasn't a floating agitator and it was a fixed position, which caused us to lose some of this data, some of this flat line that we have going on here until the issue was corrected with the pit volumes. So that's why we weren't able to use a lot of mass spec data on the evaluation, just because there wasn't enough there and we didn't want to get biased with speculation and hypotheticals. We really wanted to look at what the rock data was telling us about this regression and how it was affecting our the potential production. So I like looking at these. This is really the oil fields version of a starry night. There's a lot to see. There's a lot to take in. I know there's a lot of data saturation when it comes to petrophysical models. But the key components I want to show here and why this petrophysical models are important in conjunction with the rock data is once we start applying this data, we can really evaluate and see differences when it comes to our fluid saturations, what our porosity is looking at, especially in the organic porosity. You know, we applied the TOC numbers, which were a little bit lower, that allowed it to give it more organic porosity that was being filled up by hydrocarbons. This was done with the lithoscanner as well. So we compared what the lithoscanner was saying versus our XRD data, and we had a relatively good match with the B clay numbers. So the triple combo information was matching it with the actual physical rock data, which was nice. And we were able to apply this and fit the curves with each other. Now, what we see for our two different zones is we have some water saturations here, which is this light blue color, but we have some great volumes for production. And same way with this zone. I've actually kind of highlighted this whole bottom section, so it's just that one zone. So this allows us to really hone in on these two zones and focus more than just looking at the Tmax by itself. And so when we have these two different sets of information applied together, it's going to help us better evaluate what's going on. Now, as far as the Tmax and its effect on production, that's an ongoing thing that we're working with the operator on. But the initial production wasn't far off of what they anticipated as far as their production. Also, through our research, we came across some unpublished papers, and that's why I don't have this information in here, is because it's not published yet, of same lab experiments with the Monterey shell and them applying a water function to this that basically insulated the organic components and only allowed the kerogen to produce light end members of hydrocarbons. So that's something that we didn't see in this well. We definitely see the heavier components, as I had mentioned earlier, with the Hawk PAM information. And it didn't affect it large enough to deter this client from working in this acreage. And when we looked at other wells, this was definitely an anomaly as far as it came to this regression. But it was something that was exciting and important to us for the sole fact that none of us have really seen this. This is a first occurrence. And when you have a tight data set like this, it really highlights the importance of not taking the data at surface value and kind of exploring it a little bit more. Because if we hadn't seen that, we wouldn't have known how much effect the Tmax had just due to our clay content, but just the effect of the heavy hydrocarbons as well in the kerogen peak. A lot of us just look at this information and say, great, I have 4%, S2, I'm great, this is perfect. When in reality, it can actually be a lot lower as far as an immobile component for hydrocarbons. So just kind of wrap everything up. The heavy hydrocarbon constituents had a 2-degree change to the Tmax, not large enough to be overly concerned for ourselves. I mentioned before that S2 peak really showing the true kerogen potential when we used Hawk PAM and allowing us to break these immobile components off that are polar and somewhat difficult to get off with DCM. Really, the total clay was the main driver here for the Tmax regression, but it was the smectite percentage that was the primary driver, causing upwards of 5-degree changes. And then the last point before we kind of start talking about questions and get into some more details is, combining that cutting analysis with that petrophysical model allowed us to be more accurate in our interpretation, especially when we're looking at production and economics. So combining these two things together to give us a full picture allowed us to understand that, yes, we have a Tmax problem here, but we applied that to our Wolfcamp model and the petrophysical model, and it's not going to change our production to shy us away from being able to continue with this project. So lastly, just want to thank a few people. Matthew Riley with Huntington Energy Albert with Wildcat, and Wes Ingram. Wes Ingram was the one that put the petrophysical models together for me on his spare time. So if it wasn't for these gentlemen, I would still just be looking at an Excel sheet right now. So I really do appreciate you letting me share this. I'm looking forward to the questions you have. Thank you.
Thanks, Nick. That was great. With that, we'll open it up to questions. We haven't gotten any questions yet, so we'll give people a couple minutes to see if they come up with any questions, and we'll go from there.
Perfect. This is usually when I joke with people, and it's difficult, so I apologize, everybody.
Well, we haven't gotten any questions yet, so I'm gonna guess that we just don't have any. So with that, we will say thank you so much, Nick. That was fantastic. You guys kind of come up with questions in the future that you want to ask. You can get a hold of Michelle, and we can get you in contact with Nick. And thank you again. Really appreciate it. And we hope to see you guys all again at our November technical luncheon. Thanks again.
Thank you.
Thanks.